for coming for the second talk late in the day. I want to, in this talk, explain a few elements of the proofs of the bulk statistics result that I had from the previous slide. And okay, so let me just remind you what this bulk statistics result was saying. So fix a simply connected Gothic R, which is my macroscopic domain. I fix some large integer n and a tallow domain given by this Roman R that kind of approximates this macroscopic domain. I let m of n be some, or m be some random tallying of my big domain, and I fix some point v in this macroscopic domain that who's such that the gradient of the limited shape is s comma t, and that's kind of in the liquid region in the sense that s and t are positive, and 1 minus s minus t is also positive. So I have kind of a non-trivial proportion of all different tiles. I'll also pick a point v, which is again eventually going to be the point in which I'm zooming into, that approximates this Gothic v. Okay, and again, the question is, what is the probability of seeing a given pattern of tiles in a bounded radius of this point v? And the way in which we formalized that question was by taking a slowly growing neighborhood of this point v, so restricting the tiling to that slowly growing neighborhood yields a tiling of the full lattice, and the local statistics refer to the tiling of this infinite domain. And the statement was that as n tends to infinity, these local statistics converge to one of those mu st measures. Okay, and what I'll try to do in this talk is explain a few elements of the proof of this theorem. But before I get there, I mentioned before a lot of these exact computations, and I feel like any talk about dimers or tilings would not be somehow complete without at least explaining where they come from. So I'll have one slide explaining where these determinants, at least one of many different sources for where these determinants come from. And then I'll explain, I'll go back to the basic arguments. So let's say I fix some tallable domain R, okay? And I can view it, since it's tallable, I can view it as a bipartite graph. So I mean, I've drawn sort of red and blue vertices at each face. So the faces now are vertices, and edges between vertices are exactly the dimers, are exactly the tiles, okay? I'll let this A of R denote the adjacency matrix. So for example, 1 is connected to 1, a red 1 is connected to a red 1, and a red 1 is connected to a red 2, so there's a 1 here and a 1 here. You can keep going. So AR is this adjacency matrix. And a basic fact, I mean, is that the number of tilings of your domain is the permanent of this matrix. This is not a particularly deep fact. By definition of the permanent, basically, yeah, it's basically just by definition of the permanent. I mean, any summand in the permanent gives rise to a perfect matching of red and blue vertices, which is by definition a tiling. Okay? Now, permanents are nasty, and it's a remarkable fact that this permanent can be converted into a determinant. So this fact goes back to the work of Temperley and Fisher and Castellan back in the 1960s, who basically said that the number of tilings is not only equal to the permanent of AR, which I can't do anything with it, but is also equal to the absolute value of the determinant of AR. So once you realize that this is true, the proof is not particularly deep. So I mean, the proof is just based on the purely combinatorial fact that if I expand the determinant of AR by almost miraculously, everything has the same sign. So the permanent and the determinant are going to be the same. You can convince yourself in this example that all of these guys have negative sign if I take the determinant of this matrix. Okay, so this is a counting statement, and my goal was to do probability. But now counts, I mean, you know, probability is just division of counts, right? I mean, I count something and I divide by all of them. So, I mean, you can basically divide by 2 determinants and you'll start getting probabilities. So if I actually ask myself for the probability that the random tiling contains some lozenge ij, so I comma j just means the lozenge connecting a red I and a blue j, it's given by the inverse of A of R evaluated at the entry ij. So the inverse should hopefully make sense. This is coming from a kind of Cramer theorem, right? So I mean, the division of 2 determinants will give me an inverse matrix entry. So more generally, if I ask myself, what's the probability of seeing a given set of tiles, like I1, J1, I2, J2, et cetera, it's equal to a corresponding minor of this inverse AR matrix. This inverse AR matrix is commonly referred to as an inverse Castellan matrix. So this is looking pretty good, right? If I want to compute probabilities, I really need to compute the entries of basically this AR inverse. This is particularly well suited if you can diagonalize AR. And this is why the torus is good. This is why the torus is one of the first examples to fall. Because the torus is translation invariant, which will make your AR translation invariant. That will give yourself a Fourier eigenbasis for AR, and then you're in business, right? I can diagonalize the whole thing. Okay? And it's possible to also play this game with substantial increased difficulty on other families of domains, such as the hexagon, where you can compute these probabilities through determinants again. The underlying mechanism is some sort of modern mechanism is somewhat different. But at the end of the day, you'll get that local probabilities are again given by some matrix that's a priori somewhat difficult to, by some matrix. Now, this is perhaps, if you see this at first, you might think that you're kind of done, right? I mean, all you need to do is compute the inverse Castellan matrix. As I was mentioning in my previous talk, this is a fairly involved task and practice. This matrix, in particular, this matrix has to include all those limiting statistics that I had mentioned from the previous slide. You have to be able to see from this inverse Castellan matrix this sort of degenerate variational principle, these discrete sign kernels, this sort of airy line ensemble. All these things have to be hidden in this inverse Castellan matrix, which should at least give you some clue that this is a very deep and non-trivial object. So properly pushing through this procedure on any domain, you should expect to be fairly non-trivial indeed. Okay. So now, again, I want to go back to, I can go on and on about the story. It has a lot of deep, beautiful algebras, connection to representation theory. But if I continue down that road, I will not get to the theorem I promised to get to. So let me switch gears and talk about what goes into the proof of that universality statement. Okay? So this universality statement, it will proceed by, as I mentioned before, a kind of comparison. I'll compare the tiling on a general domain to a simpler object, which I have an algebraic handle on. And that simpler object will be a certain family of non-intersecting paths. So before I describe that simpler object in more detail, let me just make a brief digression into non-intersecting paths. So a path is simply an integer sequence, q0, q1, all the way up to qt, so that q either stays the same or goes up at each step. So you should view kind of it going left as staying, so that the axis is like pointing this way, right? So this you should view as being the same. This left step you should view as staying the same, and the right step you should view as going up one. And an ensemble, a sequence of paths, a family of paths is called non-intersecting if it remains ordered. Okay, so I mean in particular, if they start out ordered and they remain ordered, then the paths the paths can't intersect. Okay, so I've drawn an example of a family of non-intersecting paths to the left over here. Okay. And now there's a bijection between non-intersecting path ensembles and Lozenge tilings. So basically what you do is you take any step of the path and you kind of just fatten it up. Like just imagine you make a little, you just kind of make a little rhombus out of it by translating a little bit to the left and right. And that will give you a sequence of lozenges that either look like, that kind of either point this way or point this way. Okay? Okay, so this will at least fix kind of the locations of the horizontally pointing lozenges. And then the rest, whatever part of the space you have not filled in with these lozenges, you just place the vertical lozenges, okay? So whenever I have a family of non-intersecting paths, I can recover from it a lozenge tiling, and this procedure is completely bijective, it can be reversed. I just kind of take the midlines of any of these horizontal pointing lozenges and I'll get a family of non-intersecting paths, okay? So there's a bijection between lozenge tilings and non-intersecting paths run for time t. So I can look at lozenge tilings on kind of a strip of height, in this case 5, and this can be viewed as a lozenge tiling on a strip of height t. Okay, so these, Okay, so now this is all deterministic. Again, this is nothing random here. So what I'm going to do, since this is a bijection, random lozenge tilings directly give some measure on non-intersecting paths. But I'll construct a different measure, a not priori different measure on non-intersecting paths, which is more accessible, which is more solvable, and then I'll compare the two models. So that model was introduced by Koenig, O'Connell, and Rock, or at least it was studied in some level of detail by these three authors around 20 years ago. And it proceeds as follows. So we'll fix some initial conditions. So you should view this A. I should imagine that you have n paths, little n paths, and this boldface A is the initial data. It's where the paths all start. Okay, so I have A1, A2, all the way to AN. Okay, and then what I'll do is I'll consider a probability measure P. I'll call it P beta of A. A is indexing the initial data. Beta is indexing sort of the drifts in the paths, which I'll explain it more in a few moments. So it's a measure on this non-intersecting path ensemble Q. Okay, so the measure is defined as follows. So each Qi is one of these is a Bernoulli random path. So it stays put with probability 1 minus beta, and it jumps to the right with probability beta. Okay, so each one is individually that. Each Qi starts out at AI, but then now I'm going to do something non-trivial. I'm going to condition. So I'm going to condition on these paths to never intersect. Okay, so that by definition will give me some random non-intersecting ensemble of paths. Okay, so for those of you who've studied Dyson-Brownian motion, this is the completely discrete, this is the fully discrete analog of Dyson-Brownian motion. Okay, now you can write down the probability. I mean, I've kind of described it in this conditioning in terms of conditioning, but you can define, you can write down its probability density function somewhat explicitly. I've written it down over here. I won't really use it much in this talk. I just wanted to let you know that it's explicit. Now, a fact about this model is that I've sort of fixed the starting data, and I've run this thing. I get some, it's basically a Markov process, okay? If you fix the ending data, if I fix the locations of where the paths all end, then p beta, this measure, is uniform on all non-intersecting paths conditioned so that each path starts at AI and ends at QT. So you can view this as you can view p beta a as a random tiling on some vertical strip of height A, where the bottom boundary conditions are fixed by A and the top boundary conditions are random. Okay, so you kind of randomize over the top boundary. But if I condition on the top boundary, then it will become uniformly random Lawson tiling once again. Okay, so why are we doing this? Why am I referencing this model in the first place? It's because it's sort of more amenable to an algebraic approach. Okay, so this model, so it's a theorem of Gorin and Petrov, is that this model, first of all, it's a determinable point process, but more importantly, the matrix, called the correlation kernel, or the matrix of this associated with this process, is amenable to analysis. You can actually do asymptotics on it. You can take limits with this thing. It's expressed as a double contour integral, so you can do some kind of steepest descent on it. I have not written down the formula, but it is, one can write it down. It's 1 or 2 lines long. Okay. So now, what you can do is you can start to analyze this matrix and therefore this model. You should view this model as almost completely under control. And the statement that's relevant for this talk is the following analysis the following result that these authors have obtained by analyzing this matrix. It essentially says the following. So if the initial data, sort of in broad terms, it says the following. So if the initial data is sufficiently regular, so if this A is sufficiently regular, then you should expect to see these mu-st local statistics appear after running this p beta, after running these non-intersecting walks, these random walks conditioned to non-intersect after a short period of time. So let me try to make that a little bit more precise. So we'll fix some scales, u, t, v, and n, that are kind of increasing. I have some initial data, so n is the number of paths, okay? And I have some initial data, a1, a2, all the way to an, and I have some density rho. So you should view rho as kind of the density of paths that you're starting with. So you should view a as kind of starting out approximately kind of Lebesgue distributed, like I have one path every one of a row steps or something like that, okay? So the way in which you kind of quantify this is you say that so this initial data a approximates Lebesgue measure with density rho on scales of size v. So if I basically, of scales of size u. So if I take some interval I in some subinterval of, like, say minus v to v. So I have some. So say I pick some point x naught here. I pick some interval of length 2v surrounding it. I pick any interval of size u that's contained in this interval. Okay. Then the claim is that if I intersect the initial data with that interval, then I have about rho times u many initial points. So basically, this is some kind of quantitative way in which the initial data is approximating Lebesgue measure, where the quantitativeness is governed by these scales u and v. Okay. So now the statement, the theorem is that, okay, so this is just a condition on the initial data. The statement is that if I run this random walk ensemble, this p beta a, for some time t, and so t is chosen to be between u and v. So kind of, I have a scale u on which I'm Lebesgue, and I have an interval v on which I kind of stay Lebesgue. So if this t is kind of between them, then these random walks, I convert them into Lozenge tiling, and this Lozenge tiling will have the correct limiting statistics. Okay, so this is a way in which you're seeing these limiting statistics arise coming from this Markov process. So I should mention that this is a discrete analog, and I think it was very much inspired by the works of Landon and Yao, Ben Landon and Neishi Yao, and also Landon, Sosui, and Yao for Dyson-Brownian motion. You can view it as a fully discrete counterpart of it. Okay, so now with this in mind, I will try to outline how one will proceed with proving these statements. Okay. So again, to remind you, we start out with a teledomain Roman R, which is again some like sort of blow up of some macroscopic domain Gothic R. You pick some uniformly random tiling of it given by this M. It has a height function H, and you pick a vertex V, which is approximating some some macroscopic vertex V, given by this Gothic V. So again, the game is to locally compare the tiling, the sort of complicated tiling of the original domain M, with one of these p beta A's, with one of the things I can kind of get my hands on. Okay? So this will proceed in 3 steps. The first will be your algebraic step. The second will be a probabilistic step, and the third will kind of be importing these. The third will be kind of importing the algebraic step from the previous slide. So so the first step is what's often referred to as a local law. So what you'll show is that H on local scales, if I look kind of locally, H is again a random height function. But what you'll show is that it's approximately planar, so it's approximately linear, with a certain slope in small disks around V. So what this will eventually do in practice, it will verify this condition here. It will verify the regularity of the initial data. What you'll see is that the locations at these starting points are going to be approximately linear. This local law will basically verify that the initial data here is approximately linear with a given slope. Okay. The second step is a comparison statement. So what you'll do is you'll find a way of coupling the tiling on your domain R with one of these p betas in such a way that these models coincide around the point V that you're looking around. So this is kind of showing you that the local statistic that the 2 models, at least locally, are behaving in the same way. And then you conclude by using more or less importing the result from the previous slide. Since the p beta model, since this p model had the correct limiting local statistics, you deduce that the same will happen for your original model M. So I should say that this is somewhat reminiscent of this 3-step strategy of Xiao, who proved universality results in random matrix theory. It takes a significantly different flavor, though, because I mean you have a matrix model in your case. Here you have tilings, and the 2 objects are basically completely different. But sort of the underlying, I mean the philosophy, or at least some of the physical phenomenology, is analogous in both situations, and we're kind of trying to exploit that as much as we can. Okay. So what I'm going to do is I'm first going to state what this local law is. I'm then going to try to outline how this coupling works. And then I'll say a few words on how you prove this local law. Okay? So the local law is kind of this analytic step again. So I remind you that the limit shape statement said that this random height function h of n approximates the limit shape h on scales of order n. So another way of saying that is that this h of n is something like n times this limit plus some little o of n. Okay? So you can think of this as saying that hn approximates this calligraphic h on scales of order n. So like if I look on a little disk of size epsilon n, then these things are the same up to some little o of n. But if I try to decrease the size of that disk, this error could wash away whatever approximation I have. Okay? So the local law will try to give you a way of approximating this h, try to see this approximation on much smaller scales. Okay? So keep in mind that around any vertex V kind of, where h is smooth, or at least differentiable, this calligraphic h is basically, almost by definition, approximately planar with the slope given by the gradient of h at V. Okay? So I mean, basically locally, h looks basically like a plane up to some error. What the local law will do is that it will say that the same is true about my random height function h of n. So more precisely, the following statement is going to hold. So I'll fix some constant c, which is explicit as something like 1 over 100,000. It doesn't really matter. And I'll fix some scale. So m is going to be the scale, okay? And it's going to be, say, anything between 1 and n, basically, okay? And now I look at the following. So I fix my vertex v is fixed, remember? And then I look at all the vertices u in some m disk around v. So the picture is, you have your domain, which is fairly complicated. I fix my point V. I look in some disk. The whole kind of diameter of this whole domain is like n, and I'll pick my disk of radius m. Okay, so U will lie somewhere on this disk. Okay, and okay, so now if I subtract HU from HV, the statement is that this is approximately given by U minus V times the gradient of this limit shape. Okay, so this is giving you kind of the planar part. And the error when you do that is tending to 0. It decays like a power of log. And this all holds with very high probability. Okay? So another way of saying that is the probability that this is too big is very small, okay? Which is what I wrote over there. So here, the key point, which is why we call it a local law, is that this M is independent of N. I can take, although, I mean, previously this error had some N dependence in principle. The size of this domain M, of this disk M, can be taken basically almost to be of order 1 size. Okay, so you're really probing the tiling on very local scales. So if I take M to be very large, say of order N, I'm kind of giving a global approximation for the height function. But if I take M to be basically of order 1, I'm getting a local approximation for it. Okay, so now let me outline how the comparison works. So we'll fix a vertex V0 in R, as I've always been doing. Okay, and I'll fix some integer t that's kind of lying between 1 and n. Okay, so n is again the size of the domain. I'll fix a vertex u, which I'm basically going to take v and I'm going to step back by t. So I'm going to kind of give my walks room to run, right? So so here's a picture. You have a vertex v, and you're kind of stepping back a little bit by t to get a vertex u naught. Okay, and now we'll interpret M, again, just using the bijection from before, we'll interpret M as an ensemble of non-intersecting paths. Now this ensemble will not be this p beta a thing. It will be some other random ensemble, but it's going to be some family of non-intersecting paths. And we'll let this boldface lowercase q mark where these paths intersect this line, basically. This is going to be the initial data. So I'm going to kind of condition on this initial condition. So the local law now is going to give you a few things. The first thing it's going to say is that so I have a bunch of walks here. The local law is doing, again, a few things. So it's first of all controlling this initial data, and it's also controlling the drifts of the paths. So I mean, this might not be a priori obvious, but you can kind of, going between the bijections between tilings, height functions, and paths, it's not so hard to see that that this kind of control in the height function is basically controlling where the paths start and how they drift. Okay? So now what you're going to do is you're going to introduce 2 different initial conditions, which are going to eventually sandwich your tiling configuration. So the initial data are going to be the following. You're going to introduce initial data P and R that coincide with U around, again, U is kind of the step back point, coincide with U coincide like locally around U, but then they kind of are to the left and right of U, of Q away from U. So it's more easy to just see it from the picture. So Q, which is the thing you got from the tiling, is in the middle, and P and R are on the top and the bottom. The white vertices are where everything matches, and the black vertices are where they differ. So as you can see, they match in the initial conditions here given by these dots. They match in these white regions that are near U, and to the left and to the right of U, they'll be slightly shifted. So P is going to be a little bit shifted to I guess the left, and R is going to be a little bit shifted to the right. Okay, so I've just taken my initial data, matched them near U, and kind of shifted them a little bit to the left and right of U. And I'll define 2 numbers, beta 1 and beta 2, so that they're equal or approximately equal, but so that beta 1 is slightly less than beta 2. So P, and I'll consider these 2 measures, these 2 path ensembles, P beta 1 of, I'll consider these non-intersecting paths, P beta 1 of P and P beta 2 of R. So since the initial data of R is to the right of the initial data of P, and also since the drifts of R are beta 2, which is bigger than beta 1, I should imagine that the paths in R are moving faster to the right. They're sort of to the right of the paths in P, okay? And I'm going to try to sandwich Q in between them, okay? So what you're going to do is, the first thing you're going to do is you're going to show there's a coupling between P, Q, and R so that Q is bounded between P and R. So that's kind of the first step. The second step is to show that so now P and R, if I do that, then I'm actually in pretty good shape, because P and R are again coming from this P beta A ensemble, which, as I mentioned before, I can analyze to my heart's content, right? I have formulas. I can really say almost whatever I want about this model. So what you'll do next is you'll show the expected difference between P and R if you tune the parameters correctly. The expected difference between them is very small. So this is again based on this part of the coupling is based on exact formulas, although it might be possible to reduce that to some extent, but I mean, yeah. But this coupling here is based on exact formulas, and the fact that kind of, first of all, that beta 1 and beta 2 are close as I imposed, and also that P1 and P2, sorry, P1. This should be P and R. These P and R are pretty close because they're both given by Q near U naught. So the fact that they coincide nearly around U, that they coincide near U naught, and the fact that their drifts are almost the same but slightly not, well, allows you to show that in kind of some shaded region, the shaded region, P and R have low expected difference. But now since P, Q, and R are ordered, if P and R have low expected difference, that means that P and R are probably going to be equal. I mean, since they're ordered, if I have 2 numbers that are ordered and their difference is small, then they have to be close to equal, basically. So they're going to be equal in the shaded region, and since Q is sandwiched between them, Q also has to be equal to them. So that's how you're going to eventually couple Q with P and R, and both P and R are kind of fair game for which you can start to analyze because they're algebraically simple or given by this P beta A ensemble. Yeah.
Is it because you know the boundary, you're matching the boundary conditions?
Yeah, you're matching them kind of locally around U naught. So that's. Yeah, that's what you're also kind of using the fact that the drifts are close. If these drifts were too different, then they would have no shot at being close to each other either. Yeah. Yeah, any further questions? Okay, so I will keep going then. Okay, so now I want to talk about the local law, the sort of statement that on local scales, my random height function is approximately planar with the right slope. So again, I'll remind you of the notation. I have this limit shape calligraphic H. Its gradient at my point V was given by this ST. I have the scale M, which can be, I really want to think of M as kind of like log n or log n. So you think of M as very, very slowly going to infinity. So like, yeah, again, n to the delta, log n, log n. This is the kind of thing you want to think of M as being around. Okay? And the statement is that if I take differences between points in this disk, of radius m, differences in the height function, then it's going to be approximately linear with the slope given by what it should be, namely the gradient of the height function. Okay? So the proof of this theorem will proceed by a trick that people, a framework or a method really that people often like to use in analysis, induction on scales basically. What you'll do is you'll repeatedly apply the global law on smaller and smaller domains. So you'll kind of shrink the domain, apply some variational principle, apply some kind of global law, do it again and again and again, and shrink the domain bit by bit. Okay, so the issues with this is that it will require an effective limit shape result with explicit error rates. So I need to actually quantify the rate of convergence. I'll need to quantify, in particular, this little o of n. So that's point 1 that I'll need to do. And point 2 that and this is somewhat tricky because the original proof used compactness in a somewhat non-trivial way. So that it didn't actually give quantitative control there. And point 2 is that I'll need to ensure that as I keep on shrinking the domain, the slope, the gradient does not change too much. So let me set this up in a little bit more detail. Okay, so an effective global law, I'll just give you terminology. An effective global law is one of the form. So I know from this law of large numbers that if I scale down this random h by n, I should get a limit shape. So they should converge. This should converge to this with high probability. Okay, but an effective global law basically makes that effective. So it gets some explicit error rate. So what it's basically doing is it's saying that if I scale down the random height function by n, it's within the limit shape by some explicit quantity omega of n, as with very high probability. Okay, so ideally you might want to take omega n to be something like 1 over some power of n, or maybe some inverse power of n, or maybe some inverse log power of the log n, or something like that. Okay. So again, so h is given by the minimizer of some variational problem, which satisfies a degenerate elliptic PDE. And Concatenated prob basically told that you can take omega of n to be any delta without letting delta tend to 0. So like any fixed delta, this will hold. And my goal again is let this delta tend to 0. And I've called that delta, maybe I should have called it delta n, but I've called it omega of n. So to simplify things in this talk, what I'll do is I'll outline what to do if you have control, if you have the statement that omega of n is decaying like an inverse power of, decaying like log n to the -1 minus c. Okay, so I'm saying suppose you have that kind of control. And the conjecture, the conjecture that's been basically proven on any solvable domain for which you can compute things fully is that you should be able to do way better than this. You should be able to take omega of n to be n to the delta -1. So just like almost 1 over n basically. And I'm asking for basically 1 over log n. So a caveat, which is almost an embarrassing caution, or a caveat, is actually I don't know how to prove this statement. So even though I have a ton of room here, I mean, like this is very weak in comparison to what you expect. I only know how to show the weaker bound that omega of n behaves like log n to the -c for some c that's less than 1. Okay, but it's possible to work around this. But I won't do that here, and I'll still instead kind of pretend that you have this, and work from there. Okay, so I'll start to now describe how this proof will go. So let's say we have this original domain R. Just for diagrammatic purposes, I've drawn a disk here. Let me call it R upper 0 or R superscript 0. I'll just pretend it's a disk, again, just for purposes of drawing things. And we'll set v, again, just by shifting, you can pretend that v is the origin, okay? We have some random height function on this full domain, and it has some boundary height function, okay? And I'll let R1 denote the place, so R1, R upper 1 is the location where basically it's the half of this disk, right? So it's the location where the ball, it's the domain obtained by intersecting the disk of radius n over 2 with your triangular lattice. And I'll let h of 1 denote the restriction. So this is going to be random now. So I have a random height function on this R. You take this height function and you restrict it to the subdomains. This is going to give you a random function h1, okay? Now I'm going to condition on kind of the gray part. I'm going to condition on everything outside of R1 but inside of R0. This will give me, I'm kind of fixing what all the tiles are doing outside of here, equivalent, I'm fixing what the height function is doing there. And then by this conditional uniformity thing, I get something uniformly random. I get a uniformly random height function. I get a uniformly random tiling in this white region. So the restriction of h to R1 will give me a uniformly random height function of this R1, which has this boundary condition h1, okay? So now I will apply the variational principle twice, basically. I'll apply this effective variational principle twice. One on the big domain and one on the small domain. Okay, so I'll let h, so I need to set up a little bit of notation to do that. So let h naught denote the solution to the variational principle in the big domain, namely the variational principle on this disk with boundary condition given by the correct scale of this h0. And I'll let f of 0 denote the solution to the variational principle, the limit shape on the smaller disk with this boundary condition given by h1. Okay, and what this effective variational principle allows you to do is it says that, okay, so first thing it says is that since h1 is coming from the original height function, I know that this h1 is close to h0, right? It's close to the solution of the variational principle of the big domain, right? Because h1 by definition is coming from this capital H. This capital H has an effective variational principle. It's saying that capital H is close to h0. So a special case of that in particular is saying that h1 is close to h0. So on the boundary condition, you're close to this h0, but you might not be exactly equal to that. Your error is this omega n, okay? On the smaller domain, what I know is just, again, by applying this effective variational principle, what I know is that, maybe this should be a n over 2 inverse instead of n inverse. What I know is that the height function here converges to f0. So these two are obtained by this effective variational principle, and the omegas, the n in the second omega is halved because the size of this disk is halved, okay? Okay, so now what I'm going to do is I'm going to iterate. I'm going to keep on iterating this task. This is induction on scales, basically. You rescale. I've given us somewhat involved picture here, but really you just think of it as you rescale. You rescale this white region up to get the whole disk again. I cut out half that region and I keep iterating. Okay, I'll give you some kind of fancy notation here, but that's all I'm doing. Okay, now each time you do this, the boundary conditions differ a little bit. I mean, I have this h1, this new boundary condition. It's not exactly determined by h0, right? It's close to this h0, but it's not exactly equal to that. I had a little bit of error at each step. Okay, in particular, so that's what I've written here. The boundary conditions, if I kind of iterate this at the kth step, I call that hk. The boundary conditions of hk and hk minus 1 are slightly different. They're off by omega n, or maybe omega n of k, or n over 2 to the k, or something like that. So the boundary conditions are slightly different. And I have to make sure that this doesn't mess things up. And the way in which you make sense of that is you need to make sure that the gradient doesn't change when I keep on making my scale smaller and smaller. I need to make sure that the flatness, sort of the gradient of my limit shape around the origin doesn't change too much as I go deeper and deeper down. Okay. Okay, so this is now an excursion basically into elliptic degenerate. In fact, degenerate elliptic PDE. It's a purely deterministic fact about how solutions to this variational principle change if I poke the boundary conditions a little bit. Okay, so so let me just set things up a little bit. So again, the game is to bound the change in the gradient when I pass from h to f, or maybe more generally hk to hk minus 1, if I just zoom in one step. So the statement is the following, it's in this lemma. So I suppose that h1 and h2 are two solutions of the variation principle with boundary conditions h1 and h2. So again, you can completely forget about tilings for now. Then there exists a constant c, which depends on kind of how close how liquid you are, right? I mean, I impose that ST and S plus T are both strictly, S plus T are strictly between 0 and 1. It will depend on how close you are, how degenerate you are, basically. So that the following holds. So you imagine that H1 and H2 are kind of close to a plane. I mean, you have a little bit of wiggle room here. Then what you're basically saying is that the gradient of H1 and H2 is close to the difference, the maximum difference between the boundary conditions, okay? So this statement, it's basically, well, I like to think of it as a C0 to C1 bound. You're basically controlling, on the right side, you have a difference between the C0 norms of your two solutions, and you're deducing from that a gradient difference, a derivative bound, a C1 bound. Okay, this does not hold for general functions. It usually goes the other way around, right? If you have a gradient bound, then you can usually deduce from that a C0 bound. Now you're doing the opposite, and this very much uses the fact that you're dealing with the solution that your h's here are coming from the minimization problem to a certain variational principle. Now, if this variational principle were sort of uniformly convex, if H satisfied a uniformly elliptic equation, this would follow from classical results in the elliptic regularity theory. I mean, the buzzwords of the shadow estimates and an interpolation bound. In fact, I've not actually seen this result, even in the uniformly elliptic case, appearing anywhere in the literature. I even asked some people about it, and they didn't know offhand. But this is not such a jump in terms of what was known from the classical theory. Now, the problem that you actually have is that H satisfies a degenerate elliptic equation. This equation is not strictly convex, so you have to use some regularity estimates that are somewhat more recent, not 60 years old by this point. I mean, fairly 15 years old, by De Silva and Savin, in order to prove this lemma. Okay, but now you imagine that you have a lemma like this. Now we can start to make sure that the gradient is kind of stable, that the gradient doesn't change too much as I decrement the scale. Okay, so again, I remind you that I had kind of the solution to the variational principle at the kth iteration was given by this HK. This effective variational principle tells me that HK minus 1 minus HK is at most given by this omega of nk. Okay, and the stability estimate is telling me that the gradient of HK minus 1 minus HK is given by basically it bounds the C1 norm by the C0 norm, right? So it tells me, in particular, if I apply this line here, it will tell me that the difference in the gradients is at most some constant times omega n of k, okay? So now my goal was to keep going down until I reach scale m, right? I wanted to get this diameter m. So let me just call k the number of times I have to half myself to get there. So k is the number of times I have to half n in order to get m, okay? So now let me see how different is the gradient of this limit shape on the kth level, which is really probing things on scale m, to the original thing st. So by definition, st is equal to the gradient of the original limit shape at 0, 0. Okay, I can just by triangle inequality, I can sum up over the consecutive differences between the gradient of hk and hk minus 1. I apply the C0 to C1 bound to bound this by a C0 norm of hk and hk minus 1. Then I apply the effective variational principle. This should be omegas instead of pi's, I guess, but to get this bound here, which is saying that this is bounded by the sum of these omegas. Okay, and now you can start to see where the log n this log n to the minus 1 minus c comes in. K you should think of as m. You should think of as almost order 1, which means that k is like log n-ish. So if I want to sum up log n things, and I want this thing to be very small, I need these guys to all be smaller than log n. Okay, so in particular, if this omega k is like log n to the 1 minus c, you can sum this series and you'll get this error of log m to the minus c. And that's, this is hopefully familiar from the local laws. This is how you get something like that. Okay, and this hk, just to conclude, to finish off, this hk is going to be approximately linear with the slope. So by this variational principle, I know that the original random limit shape is close to hk on scales of order m. And this will give you this local law. Okay, so just to conclude, in the previous talk, I talked about universality of various statistics. In this talk, I tried to outline in more serious detail the proof of the universality of these bulk local statistics for Lussenstellings. The proofs were based on a combination of algebra, analysis, and probability. The analytic step was coming from this local law, which combines effective variation principle, induction on scales, and gradient stability balance coming from elliptic PDE. The algebraic step came from understanding these bulk statistics for non-intersecting random paths, these p beta a measures, based on exact formulas that you can analyze. And the probabilistic step kind of glued them together by introducing a coupling between this p beta a model and the original tiling model I was interested in by sandwiching the tiling model between two of these P beta A models. And it used this analytic local law as input. So with that, I'll thank you for your attention and stop there.
All right, do we have some questions?
So you emphasize this effective estimates here. You had these explicit little c, and you had your power minus 100 on your n. I mean, did you really need to know that you had explicit constants there, or
This,
you know there's some constant?
yeah, this you just needed some constant. This one you just needed some constant.
Okay.
Yeah, it didn't really matter.
That you know what the c can be.
Yeah.
It's not that
Yeah, you know what the C can be, but you don't really need it. Yeah. But you do need to know like this. I mean, you do need over here. Where is it? Yeah, I mean, you do need to get some kind of quantitative control in this, like log n to the minus c or log n to the 1 minus c. You don't need to know what that c is, but you need to know like some inverse power of log or something like that.
you emphasized the number, but I didn't know if that.
Yeah, it's not the same. The 1 over 100,000 is not important. Yeah. No, this is actually considerably more technical. This is arguably one of the most annoying parts of the work actually. What you do is you come up with two variational principles. It's two effective variational principles. One is this one basically that holds in full generality, but you can only take the sort of weak bound. And the second is on domains where this H is kind of uniformly elliptic, where it has no frozen regions. You come up with an improved variational principle. And then you kind of stitch them together, go back and forth between the two. So it's a more complicated version of what I just said. Yeah.
Any other questions? All right, thank you.